Okay, well done, you've made it. You got to the 6th subchapter, the 6th lesson on Chapter 7, Applications of Forces for Year 13. So now it all comes together in some quite difficult problems involving connected particles, for example pulleys, where the objects are moving and also friction is in the equation too. So it's pulling together bits of Year 12, Chapter 4 of Year 13 and Chapter 5 of Year 13. And the force diagrams can get quite difficult indeed, so lots of practice is needed. In terms of what I say about lots of practice, let's start practicing already with some pre-questions, a warm-up as it were, 2 to have a go at. Here they are. Try these now, press pause, have a go on your own, see how you do, and press play when you're ready to see the solutions to these, and I'll try my best to guide you through them in a way which hopefully will make sense to you. Okay, so let's have a look together now at question 1. Question 1, we have 2 particles A and B of masses 0.4 and 0.8 respectively. These are connected by a light inextensible string. Particle A lies on a rough horizontal table opposite a smooth pulley which is fixed at the edge of the table. So we've got here that A is lying on a rough horizontal table, so let's just draw this in already. So we've got the table like so. This can be my particle A. So I'll just label this A like so. And it says here that the string passes over a pulley, and it says it also as well that A lies opposite to a smooth pulley which is fixed at the edge of a table. So an edge of a table means it's about to fall off, so this could be the edge of the table. We're told that the pulley is opposite to A, so if I just do the pulley, which will be circular in terms of just opposite to A, dangling over the edge like so. And as well, we're now told that the string passes over a pulley and B hangs freely. So I'm going to do a particle B, make this slightly smaller. That can be B, and that's dangling over the edge like so. Now I've got strings connecting them, so that goes to there, and this one goes down like so. And that's B, which is hanging freely, as it says. Now, it's a string, so we know, or should know at least, that the tension acts away from the objects in question. So acting away from A is T, acting up and away from B will also be a tension in the string. We're told as well about the weights of these. Well, we're not, but we sort of are. The mass of A is 0.4 g, which means its weight, so its mass is 0.4 kilograms, I mean to say, so its weight is 0.4 g. In the same way, the mass of B is 0.8, so this one's weight will be 0.8 g. We're also told there's a frictional force of magnitude 0.08 g, which opposes the motion of A. So I'm going to add this in as well. So there we go. So we're asked to find the acceleration of the system. Oops, that's not a very straight arrow, so there we go. That's better. Find the acceleration. Well, the acceleration, it's clear to see that this particle B is heavier than A. It's twice as massive. So the acceleration relative to A will be going this way, and relative to B will be going down. So it'll be the same magnitude, but different directions relative to A and to B. So what I suggest we do now is consider particle A and B separately, using F equals ma applied to both. So for A, the resultant force on A will be the tension pulling to the right, less the 0.08 g, which will be opposing the tension. So the overall force on A will be acting to the right, so the tension will prevail. That will equal the mass of A, which is 0.4, multiplied by the acceleration, which of course is what we're trying to find. We're told here, find the acceleration of the particle. Whereas for B, same idea, but just different particle. So for B, the resultant force will be acting downwards. Forces acting downwards upon B are its own weight, so that's 0.8 g. Opposing that motion is t, so do 0.8 minus t, which will give me the mass of the particle, 0.8 kilograms, multiplied by the common acceleration to both particles within this connected system. Now, if you look at this carefully, you'll notice if I were to add these equations together, I would be eliminating t, because t here plus minus t, that will cancel. So if I add these two together, the t's will cancel. I'll have 0.8 g plus minus 0.08 g. So 0.8 g minus 0.08 g, which gives me 0.72 g. So 0.72 g equals 0.4 of an A plus 0.8 of an A, which is 1.2 A. Therefore, finally, A will be 0.72 g divided by 1.2. So let's just calculate what this is. So 0.72 g, g can be taken as always, unless otherwise stated, to be 9.8. Then divide by 1.2. We get here 5.88 meters per second squared. So that's what we write down, and that's warm up one done. 5.88 meters per second squared. We now cast our eyes to warm up question 2. So for number 2, we've got here that Rupert takes a bus to school. After a year, he finds on average that the bus is late to school once per week. The bus company, however, changes the driver, and Rupert suspects the bus is now late more often. After the first week with the new driver, he finds the bus was late on 3 out of the 5 school days that particular week. So modelling the number of times a bus is late in 1 week as a binomial distribution, test at the 5% significance level whether or not there is evidence of an increase in proportion of the number of times the bus is late. Clearly state your hypotheses. Well, we need to remember there's always 2 hypotheses. First of all, H0, which is for null hypothesis, is what we're considering to be true. The null hypothesis is a case of innocent until proven guilty. So what we would assume is that the original case is still true. So after a year, originally, it turns out that the bus was late once per week. So H0 almost always is assuming nothing's changed. So we'd assume that the proportion of times this bus is late is once per week. Now, a school day is 5 days, so that's 1/5, which is 0.2. And I'm letting here P equal proportion of days the bus is late. So before this driver has changed, it was late 1 in 5 days. That's 0.2. That's 20% of the time. So P, proportion of days bus is late. So that's called the null hypothesis. You don't need to label in that it's called the null hypothesis. This is just to aid your revision in case you've forgotten, which you are allowed to do. You're human beings. Take it easy on yourselves to an extent. Of course, I do try to recall these facts. When I say take it easy, I don't mean literally just not to try. So H0, proportion of lateness is 0.2. The alternative hypothesis, sometimes called H1, is based off the wording of the question. So here it says that Rupert's suspecting the bus is now late more often. So the same thing again. More often means that he's suspecting the proportion of late times has increased. So his hypothesis is actually the proportion of lateness has now gone greater than 0.2. And that's what he suspects, and this is what we're trying to show or prove using this binomial hypothesis test. So we model the number of times the bus is late in 1 week as a binomial distribution. So let's do that, and we base our initial model off the null hypothesis. So what we'd assume here is that x, the number of times a bus is late, follows a binomial distribution where the number of journeys in 1 school week is 5, and the probability of a bus being late on any one of those days is just late 1 day in 5, 1 out of 5, a 0.2 chance. So that's our model which we are testing against. So what I'd suggest we do here is to sketch out our normal distribution curve. So here we've got number of late days. So let's call this x, that's number of days it's late. And of course, because we're thinking that the proportion is 0.2, we're expecting the mean to be 0.2, but actually what's going to happen is something like this. So we'd imagine that most of the time it's going to be late just once per week. And actually, we're wanting to test at the 5% significance level if this time's changed. So 5% at the later end is somewhere down here. So that's going to be 5% of the curve. Like so. So we now use our calculator to test this hypothesis. What we have currently is we know that using this new driver, the bus was late 3 out of 5 times. So we know this, so we can jot this down. So after the first week, we're told the bus was late 3 out of 5 school days. So what we can do is work out the chance of that happening, or more than those days late. So what would the chance of that happening be? Well, the probability of having that many or more days late, the chance of having 3 days late, or 4, or 5. Now, if that is so unlikely, it's 5% or less, then the 3 will be in the critical region, and therefore we would reject the initial idea that actually there's no change in the lateness. So what we need to do here is to work out the probability of, if this is true, but there is only a 20% chance of it being late, what's the chance therefore of 3 out of 5 days or more the bus being late? So the chance of it being late on 3 or 4 or 5 days, that accounts for all scenarios, everything, apart from the probability that the bus was late 0, 1 or 2 times. So that's 1 minus the probability that it was late 2, 1 or 0 times. Now, generally speaking, what I say is if we have a binomial distribution where the question can be stated in terms of an inequality, we can use the binomial CD function on the calculator. So what we do, we press menu, we go along to option 7 on the class whiz, we go down to binomial, not PD, but press down and go to binomial CD. Now importantly, when we have a question like this, we have to have it in terms of less than or equal to the value we're testing against. So if this is no good, we need to have it in this form here, where the inequality symbol is facing towards the value we're testing against. So what's the chance of having 2 or fewer late days based off of this idea? There's a 20% chance of lateness. We press 2 variable. Now we type in 2, which will work out the probability of being late 2 or fewer times. N is the total number of days. In this case, the number of days the bus goes to school in a working school week is 5 days, Monday, Tuesday, Wednesday, Thursday, Friday. And the probability of it being late for just one of those days, based on the null hypothesis, is 0.2. So we get here, but actually the chance that it's less on 2 or fewer days is almost 95%. It's 94.2-ish%. So in other words, it's almost definitely going to be late no more than 2 out of those 5 days. So this here is 0.94208. So 1 minus that, press menu 1 minus that answer we just got, gives us 0.05792. But importantly, relative to the significance level, that's actually greater than 5%. So although that's quite rare that the bus would be late those 3 times or more, only a tiny bit more than a 5% chance for happening. So it'd be quite unlucky for your bus to be that late. It's not quite as freakish as it would need to be to actually for us to reject the idea that probably this driver's no worse than the last one. So benefit of the doubt would be given. 5.7% of the curve would be more of a curve than this tiny tail. 5.7% would be just here. That's a probability of 3 or more latenesses. So 3 isn't quite in the critical region. So therefore what we'd do is we would accept H0. So based off this, we therefore accept H0. In other words, there's not quite enough evidence to reject H0. If 3 was in critical region, we would reject it, but 3 is just outside of the critical region, so we would accept H0. So you could say in brackets, insufficient evidence since 3 is not in this critical region. Four is, but 3 isn't quite in the critical region. That's about 5.7% from the red line onwards, but the critical region is only 5%, or this tail bit here. So it's 0.7% proportion of the curve here, which is just outside of the critical region. So therefore, we wouldn't quite have enough evidence to reject H0. Let's now have a look at some mechanics questions based off what I've explained we're going to be looking at now for 7.6. So the first question, we've got these dreaded pulleys once again. So we have 2 particles, P and Q, masses 5 kilograms and 10 kilograms respectively. First of all, we've got particles with masses. Let's just draw on straight away their weights. So 5 kilograms means a weight of 5g. 10 kilograms means it has a weight of 10g. So let's just draw those on straight away. We're also connected by a string. So you should know a string will have a tension acting away from each object. And because as well, this pulley, which is almost always, by the way, assumed to be smooth, the tension will be the same on either side of the pulley. So the tension will be acting up relative to Q and diagonally up relative to P. So what else are we told here? So P is on the incline, Q is hanging freely, like you can see. The plane is inclined to the horizontal at an angle alpha, where tan alpha is 0.75, as shown in this diagram. So let's just think about what this means. Tan alpha is 0.75, and we've seen this before in the previous subchapters. So I'm going to just doodle this out once again, because I don't think this can be mentioned quite enough, to be honest. So let's just get this nice and clear. Maybe a bit too big that actually. I'll flip this so it looks similar to what we're looking at here. There we go. So think about what tan is. Tan is the, oops, there we are. Tan is opposite divided by adjacent, TOA, literally. So if we have this angle here, which is alpha, which it is because it says it is, and we know that tan alpha is 3/4, that means the ratio of the opposite side to the adjacent side is 3:4. This now gives us a Pythagorean triple. This hypotenuse is 3 squared plus 4 squared square rooted, which is 5. So in other words, if tan alpha is 0.75, it's the same as saying sine alpha. Sine is opposite over hypotenuse. That would be 3/5. So sine alpha is 0.6. 3 divided by 5, if you're not sure where that decimal comes from. In a similar way, cos ca is adjacent 4 over hypotenuse, and 4/5 is 0.8. So we can use this in terms of resolving the weight, should we need, which in fact we do. If we read on, what we can see is happening here is that actually there is friction between P and Q. The system's released from rest. Now you know, or should know anyway, if this is released from rest, 10 kilograms here is double the weight of 5 kilograms. So it's fairly obvious, or should be, if it's not, that this system is going to be going straight down because this 10 kilogram weight will pull this 5 kilograms downwards. So the acceleration is going this way relative to Q, and relative to P is going up a slope like so for P. Same magnitude of acceleration, just different directions for P or Q. So because the system is moving, there will be a friction acting upon P which will be resisting the motion. So the friction on P will be acting down the slope like so. Because the system's in motion, it will be at its maximum value. So friction going down the slope will be mu times r. And r, the reaction force, will obviously be going straight up perpendicularly from the slope in this direction like so. So I'm going to label this r here. Now because we're labeling forces, and the obvious way to be doing the forces seems to be parallel to the slope, because that's the direction of acceleration, and the weight isn't going parallel nor perpendicular to the slope, the best thing to suggest would be to resolve the weight going perpendicular to and parallel to this slope. So let's try to do this now. So the weight going down will be in this direction, and going parallel will be going down in this direction. And that's what we have. If this is alpha, that will be alpha. Hello, Tallulah. The cat's come in. If you can hear or not, anyway. Hello, Tallulah. So, that's alpha, that'll be alpha 2. And what I'm going to do here is just colour code that so you can see where it's come from. Okay, say hello. You can speak? No, she's camera shy. Bye, Tallulah. So the component opposite to this angle will be 5g sine alpha. And the component going perpendicularly down will be 5g cosine alpha. So now what we can do is we can resolve forces in any given direction. Because for particle P, the tension is in a direction parallel to the plane, it's best to take the resolving in this direction here parallel. So let's first of all think about just particle P for a moment. So looking at P, we can work out a few things about it. So obviously we know we need to account for the friction, which is based off normal reaction, So the first thing I'd suggest would be to work out R. So if we consider forces initially perpendicular to the plane, so forces perpendicular to the plane for P, we can hopefully see here that the reaction, which is going perpendicularly up, must be equal and opposite to the only force opposing it, or the component, I should say, of the force opposing it, which is 5g cos alpha. So R must equal 5g cos alpha. However, using this idea from earlier about what cos alpha is, because cos alpha is 0.8, we can do 5g multiplied by 0.8, which just gives us 4g. In fact, if you wanted, you could even sub in g as 9.8 to get the numerical value straight away. That's optional and up to you. So therefore, the force of friction, which is now mu times r, that therefore equals 4g times mu. So that's going to be 4 lots of mu g. So now what we can consider is forces going up the slope. So consider forces going in this direction now for A. In fact, I'll change back to a red, away from a red to a black pen. So considering forces in this direction. So up the slope we have T. Opposing it we have two forces. We have a component of the weight, which is 5g sine theta, so sine alpha, and also we have mu r opposing it too, which is therefore minus 4 lots of mu g. And that will equal therefore the 5 multiplied by the acceleration, so that's going to equal 5a. And if we now consider particle Q, so this here is for P, if we now consider for particle Q, F equals ma, this is, if you didn't know already, I've not mentioned because I'm getting used to the idea that you're probably well familiar with this now. So if we do F equals ma for Q, the resultant force on Q will be acting downwards, that will be 10g minus T, which will equal the mass of Q, 10, multiplied by the common acceleration, which is a. So these two equations here, if we add them together, we'll eliminate T. So if we take these and plus, then the tension will cancel. So what we'll have on the left, we'll have 10g to start with. We'll have minus 5g sine alpha. Now again, we know what sine alpha is. So sine alpha is 0.6. So what we can say here is 5g sine alpha. 5 times 0.6 is 3, so that's the same as 3g sine alpha. Sorry, it's just equal to 3g. It's been a long day, please forgive me. That's just minus 3g. And then here, we can actually as well, if you want to, substitute in mu now. Mu, we actually know. Mu is 0.2. So 4 mu g means 4 times 0.2 times g. 4 multiplied by 0.2 is 0.8. So that's going to become minus 0.8g. And that will therefore equal, on the right hand side, added together, 5a plus 10a, that's going to be 15a. 10g's minus 3g's minus 0.8g's. At this point in time, feel free to use the calculator. So 10 minus 3 minus 0.8, that gives us 6.2g. So 6.2g equals 15a. Therefore, A must be 6.2g over 15, So for now, finally, we sub in what g is. G is obviously 9.8, so 6.2 multiplied by 9.8, all of which divide by 15. That's going to give us three significant figures, 4.05. So the acceleration is 4.05 meters per second squared. And we can now use this to answer part B, where we need to find the tension in the string. So we can sub in this value of A into the equation of motion for P or for Q. It's entirely our choice. It really doesn't matter which one we go for. So now we know A, which is 4.05 meters per second. We can substitute it into any one we want to. Now, I personally think the equation for Q is easier, so I'm going to substitute this in to the equation for Q to realise what T is. So B, if we sub A equals 4.05, etc. I'm doing these dots here to just make it clear. I'm not going to round the value off. So if I sub A equals 4.05 and the rest of it into the equation of motion for Q, and what I'll get is 10g minus t equals 10 times this value here. So if I multiply this by 10, obviously you can do it by just moving the decimal, been incredibly brain dead here, 40.506 recurring. Therefore, if we just rearrange this, so add t to both sides, and subtract the 40.50 number, t is 10g minus 40.50666, and so on and so forth. That's going to give us an answer. I'll just move this calculator to the side so we can see. 10 times 9.8, subtract the previous answer stored on the calculator. I get this value, and that rounds to 57.5 newtons to three significant figures. And that's the first one done, so quite long-winded I suppose, but unfortunately you need to get used to that possibility. So let's have a look now at the next one, worked example 2. So we've got here a pulley system. We've got one end of a light and extensible string attached to block A of mass 2 kilograms. Block A is held at rest on a smooth, fixed plane, so it's smooth. So here we have the luxury of not having to worry about friction. And it's inclined at horizontal at the angle 30 degrees. The string lies along the line of greatest slope of the plane and passes over a smooth light pulley which is fixed at the top of the plane. Here it is there. The other end of the string is attached to block B of mass 5 kilograms. The system is then released from rest. So modelling the blocks as particles and ignoring any air resistance, A part 1, show about the acceleration of the block B is 4/7 g and find the tension in the string. So almost a second nature now. I need to be just thinking, let's label in these forces. So forces due to weight acting on each. So this one here, if its mass is 5 kilograms, its weight will be 5g. And there'll be a tension opposing its motion. The tension will be acting up diagonally relative to A, like so. It'll be the same tension here and there. And on A, there will also be a normal reaction from the surface acting on A, going in this perpendicular direction like so. I'll label that R. And as well, need to label on the weight of A. So A has a mass 2 kilograms, so its weight will be 2g. But now what we need to do, because obviously A will feel like sliding down the slope because of its own gravity, we need to resolve the component of its weight relative to the slope, so parallel and perpendicular to the slope. So if we next just do this, and like I say, almost it should be becoming second nature by now. You should know if this angle's 30, this will be 30 degrees as well. The opposite component is the magnitude of the force, 2g multiplied by sine of the angle, so that's 2g sine 30 down the slope, and perpendicular to the slope we have 2g cos 30. Now normally I'd be thinking about putting friction in here, but because it's smooth, woohoo, no friction, so we can have a bit of an easier time of it, luckily. So sometimes with these questions I just think work out what you can work out. So finding the acceleration, all I know is the acceleration will be going down here because 5 is heavier than 2, so it'll be pulled down. So A is going down that way, and it'll be going up the slope relative for particle A, or box A. So what I'm going to suggest we do is F equals ma for both A and B. So for A, if we do it going up the slope, the resultant force will be going up the slope because it will be pulled down by this massive weight 5, which is 2.5 times greater than the mass A. So 5 is 2.5 times the mass, I mean to say, of A. So going up the slope we have T, and opposing that, minusing that, we need to do 2g sine 30. So T minus 2g sine 30 that's going to equal the mass of A, which is 2, multiplied by the common acceleration. And for B, that'll be going straight down for B. The resultant force for B will be 5g minus t, because t is acting up and opposite the direction of the acceleration. That'll equal the mass of B, 5, multiplied by the common acceleration. Again, you should see here we've got a simultaneous equation. So if we add these two together, what will happen is t will be eliminated once again. We'll then get 5g minus 2g sine alpha, so 2g sine 30, equals 2a plus 5a, which is 7a. But you need to remember, ideally, these exact trig ratios. So 30 degrees is one of these special values. The sine of 30 is 0.5. So this actually neatens up to just 4g. So 4g equals 7a. Therefore, dividing through by 7, a must be 4/7 of a g as required. That little square just means I've finished it. That's like I've proven something. Then part 2 of A, this is A part 1, find the tension of a string. So if we now just substitute this value of A back into one of these initial equations, which one doesn't matter, you can take your pick. So if I sub A equals 4/7 of a g into this equation here, then I can see that the tension will be 2 lots of A. So if I just highlight what A is, so 2 lots of A, so 2 lots of 4/7 of a g, then I can add 2g sine 30 to both sides. So if we do this, so 2 lots of 4/7 g, so multiply by 9.8 because that's what g actually is, then plus 2 times 9.8 times sine 30. This is if you forget that sine 30 is a half. If you didn't, you could just put plus 9.8, but doing it the long way, 2 times g times sine 30 is absolutely fine. You can see it's exactly 21 newtons. It doesn't say to leave your answer in terms of g. I believe the book does. That's absolutely fine. I'm not going to argue with the exam board, obviously, but 21 newtons is fine. It doesn't say to leave it in terms of g, so we're done now, and that's good. Part B, a slight weird question. This can throw people off. It'll only ever be a 1 mark of this. State how you've used the fact that the string is inextensible in your calculations. Inextensible just means it's the opposite of something like an elastic band. There's 2 things I believe you could say here. It means that, so something like we have used the fact of a string is inextensible. To model the acceleration or you could alternatively say the tension. So we've modelled the acceleration, or you could say you model the tension for both A and B is the same. So use the fact the string is inextensible to model the acceleration for A and B to be the same, or same magnitude. If you're being a stickler, you could say, the accelerations can't be the same because they're acting in different directions for A and B. So to be absolutely watertight, maybe you want to say it with the same magnitude. Tension and acceleration, one or the other just mention, for A and B, we can model them to be the same. If we didn't model them like that, you'd have like T1, then T subscript 2, which would be a nightmare to solve. You'd have more unknowns and not enough information. Finally, C. I'm going to give myself a bit more space for C. So moving on for C, it says calculate the magnitude of the force exerted on the pulley by the string. So if I just give myself a fresh slide to focus on C, the only thing we need is to remember that the tension relative to the pulley, call that P for pulley, will be acting away from it, and the tension had a magnitude of 21 newtons. Again, the book does this in a certain way, and that's fine. I'm going to mention a different approach you could use. So again, as ever, if in doubt with mechanics, if something like you have a box or a brick, almost always you can model it as a particle. So I'm going to think of a pulley over here. Okay, so that's my pulley. I'll label this P. So as you can see, it's going to have a force acting down, which is the tension, 21 newtons that way, and also it'll have a 21 newton force going down. Now using some simple trig, if that's 30, that'll be 90. This angle here is going to be 60. So we can label in this angle as 60, and the magnitude of that's 21. So if we consider components going down and across for P, so if I just take this diagram actually and move it across. Okay, so if we now do total going down, we're going to have 21, that force, plus this component of this sideways tension of 21 going down. Now, always remember, down in this case is adjacent relative to that angle, so it's going to be 21 cos 60. So 21 plus 21 cos 60 means it's an overall force of 31.5 going down. And if we think about the total just going to the left, then the left, relative to this 21, again it's opposite this 60. So this one going to the left will just be 21 sine 60. And 21 sine 60, again we can easily work out with one of these calculator things. 21 sine 60, that's going to give us 21 root 3 over 2, which we can leave in that form if we want, because it's not our final answer. So the force is something like this. So we've got going down 31.5, going across, that's wrong direction, silly me. It's 21 root 3 over 2. So the magnitude of a force, the overall force exerted on the pulley by this tension, by the string, is going to be this overall force here, which I'll just call R for resultant. So we can use Pythagoras here. So R will be the square root of 31.5 squared plus 21 root 3 over 2 squared, all of that square rooted, because it's just using this Pythagoras idea. So 21 root 3 over 2, that's my stored answer. So I'm just going to type ANS squared to make it easier. So square root 31.5 squared plus ANS squared, press equals, we get 21 root 3. And to three significant figures, that's 36.4 newtons. And that's our final answer for that one, 36.4 newtons. Let's now have a look finally at worked example 3, which again I've taken from a past exam paper. So prepare yourself, here it comes. So here's question 3. So we've got an awful big body of text. We've got two particles A and B, mass 2m and 4m respectively, connected by a light, inextensible string. Initially, A is held at rest on a rough inclined plane, which is fixed to the horizontal ground. The plane's inclined to the horizontal at an angle alpha, where tan alpha is 3/4. The coefficient of friction, we've been given that, between A and the plane is 1/4. The string passes over a smooth pulley P, which is fixed at the top of the plane. The part of the string from A to P is parallel to a line of greatest slope of the plane, and B hangs vertically below P. The system is released from rest with a string taut, with A at the point X, and with B at a height H above the ground. So some of it's been labelled already. So for the motion until B hits the ground, for A we need to give a reason why the magnitudes of the accelerations of the two particles are the same. Now for this one, we can remember hopefully what we did in the first couple of worked examples. So the key thing here is that this string is inextensible. So we just need to quote the fact that actually the string is inextensible. And that's why we can model the magnitudes of the accelerations to be equal. Let's now have a look at part B, which I'm afraid is quite a bit more challenging, but not that much more, compared to part C at least. Part B, we need to write down an equation of motion for each particle. So first of all, what we need to do is get this fully labelled. So we've got B here. We know its mass is 4m. So its weight, therefore, is going to be 4mg. Similar for A as well. So A, we're told, has mass 2m, so that's going to have a weight equal to 2mg. However, A will have a friction acting on it as well, so I'm going to draw in the friction, which will be opposing the motion. Friction will be going this way. I'll explain why. And also, as well, it's released from rest. It will start moving, so friction will be at its maximum. It will be mu multiplied by r. So why is it going this way, the friction? Well, look at the masses of the particles. 4m is double the mass of 2m, so the 4m's weight will prevail over this relatively tiny weight, and the system will be pulled this way to the left over the pulley. So the acceleration is going down relative to B, it will be going up the slope relative to A. As well as that, there's going to be a normal reaction acting upon A from the slope. So I'll label this R. Then, of course, what we need to do is resolve this weight of X into components parallel and perpendicular to the slope. We also should know almost off by heart now, if this is alpha, this angle here will be alpha 2, and this component going parallel down the slope will be 2mg sine alpha. This component here will be 2mg cosine alpha. So we need to know this really very clearly. If that's alpha, this here will be alpha as well. So next up, we just need to write down equations of motions for each particle. So it doesn't ask us to solve them, so at this point let's just keep it simple. So let's think about F equals ma for A and B. So for A, what's going to be pulling it up the slope, obviously, is this tension which needs to draw on T. So T minus the forces acting against its direction, which are mu r, which is the frictional force, minus 2mg sine alpha that'll equal the mass of A, which is 2m, multiplied by its acceleration. Similar job for B. For B, the acceleration will be going downwards, so the direction is down, so 4mg, subtract t acting against it, will be equal to the mass of B, which is 4m, multiplied by A, where A is its common acceleration. So that's all we need to do for now for part B. For part C, we now need to find the acceleration of each particle. So let's remind ourselves where we got to with these equations of motion for each of A and B. So this is what we got to. Now, normally I'll leave m, g in here in exact form until the final answer, but now if you look here, we've got some awful looking expressions, sine alpha, m's and g's everywhere. So what I'm going to show you now as an option, you can input values earlier if you wish. The first thing I'm going to mention is this alpha thing. So we've got here that tan alpha is 3/4. Now I've mentioned this before, so if we've got tan alpha is 3/4, think about what the tangent function is. The tangent function is the ratio of the opposite side to the adjacent. So if tan alpha is 3/4, that means for every 3 units the opposite side is, the adjacent is 4 units. We can now use Pythagoras to establish that this hypotenuse would be 3 squared plus 4 squared square rooted. In other words, we have a 3, 4, 5 triangle. So if tan alpha's 3/4, that's the same as also saying that sine alpha, opposite over hypotenuse, that must be 3/5, and cos alpha is adjacent over hypotenuse, which is 4/5. So what I'm going to suggest we do is we use these values to neaten up these expressions. So if we just move forward slightly with each of these, so t, now 2mg sine alpha, well, I can input here what sine alpha is. Sine alpha is 3/5, and g is 9.8, so 2mg sine alpha. If anything we don't know here is m, so we can do 2 times g, which is 9.8, times sine alpha, which is 3/5. That gives us 11.76. So this thing here is the same as 11.76 m. One thing we need, though, we need to find out what this mu r is. So if we think about this force diagram here, and think about forces going in the perpendicular direction to the plane, there's no direction perpendicular to the plane. The acceleration is parallel only. So there's a perpendicular equilibrium, if you will. So that means the reaction going up must be balanced equally, oppositely, with the forces acting perpendicular to it going down. And the only one here is this component of the weight, which is 2mg cos alpha. Then from that, we can say that F, which is mu r, we know what mu is. mu, the coefficient of friction, is 1/4. So if we were to do 1/4 multiplied by 2 mg cos alpha and just get this neatened up and looking nicer, then that will make our job overall just easier. So let's do that. So 1/4 times 2 times m. I don't do that because I don't know what m is, but I do know that g is 9.8, and I do also know that cos alpha is 4/5. So that's 3.92 m. So the maximum friction is 3.92 m. So this here is 3.92 m. And that will equal 2 ma. Down here, 4 mg, well, I may as well do the same thing, so I can do 4 times g. 4 times g is 4 times 9.8, that gives me 39.2. So 39.2 m minus t equals 4 ma. Now, if we add these equations together, again, you should notice that the t will eliminate. So we'll just have everything in terms of m at the bottom. So at the bottom, we'll have 39.2 m minus 11.76 m minus 3.92 m. So we'll have 23.52 m on the left, and on the other side, 2 ma plus 4 ma equals 6 ma. Now you can see these m's will cancel. So therefore the acceleration will be 23.52 divided by 6 and that's going to give us 3.92. So the acceleration of each particle is 3.92 meters per second squared. We're also going to use this part C to tackle part D now. So part D, this acceleration is going to come into play. This is going to be a SUVAT question next. So for D, we're told that particle B eventually hits the ground, but it doesn't rebound when it hits, and A continues moving up the plane towards P. We're told that A comes to rest at the point Y without reaching P. So we need to find the distance from X to Y in terms of H. So what I'm going to do here, I'm going to take off some of this labelling. So it's a SUVAT question. The only thing that will be affecting A will be the forces in the direction of motion to A. So I'm going to neaten up this diagram here. Even though the reaction force will still exist, it's not going to be relevant to the equation of motion anymore for particle A. F equals mu r will still be acting on it, as will 2 mg sine alpha, which will be going down the slope like so. So I'm just going to get rid of the 2 mg and the 2 mg cos alpha because the diagram just looks a bit too crowded essentially. Okay, and we need to think about this in 2 steps. So what will happen first of all is B will fall h, a distance of h to the ground. Now as B falls a distance of h, what will that mean for A is initially A will be pulled a distance of h meters up the slope. So from here to here, A is going to travel h. So in that h meters, let's just consider what will happen for particle B. Particle B's motion's easier, it just goes vertically down. And because the string's connected and taut until the very instant where B hits the ground, the speed of A will be the same as the speed of B. So let's apply SUVAT for B when it falls at h meters. So falling h meters, if I take down as positive, it's going to fall h meters. It was released from rest, so its initial speed or velocity was u. Its final speed is what we're really interested in. The acceleration we worked out from before, so what was it? Let's remind ourselves. It was 3.92. So acceleration 3.92. How long does it take to reach the ground? We don't know, we don't want to know, we don't care, so cross that off. So what equation of motion does not involve t at all, which will help us to find v? I'd suggest what we can do here is use v squared equals u squared plus 2as. So that's going to be 0 squared, which is just 0. So it's going to be 2 times 3.92 times h. So that times 2, it's going to be 7.84h. So therefore v, after h meters, will be the square root of 7.84h. So again, just trying to neaten up this diagram slightly. After it's travelled h, the string will become slack for this particle. So the tension, essentially, the tension won't be there. It'll be slack. So the tension will disappear because it will no longer being pulled down by B. B's hit the ground. Okay, so it won't be pulling it down anymore. The string will be slack. So after it's travelled h, they'll then keep rolling up a bit before stopping instantaneously, then rolling back down under gravity with the help of this friction, speeding up its stop. So just focusing purely on A now. It gets to h, gets to this distance here. It'll then carry a further bit up until it gets to this point here, y. At this point, it's going forward with a speed of root 7.84h. When it gets to y, its speed will be 0. So now what we need to do is apply an equation of motion for A when it gets to this point here. So it's not x, it's not y. I'm going to call this point here z. I know it's confusing because it goes x, z, y, but forgive me. So particle A consider it between z and y. So again, SUVAT. So at z, at the moment after it's travelled h up the slope, z is just where B has hit the ground. That's at that instant where B hits the ground. So the velocity of A at this point here is root 7.84h. That's the initial velocity. We want to find out how much further it goes up the slope. So what's its displacement? I'm going to also take here, up the slope, to be positive. The final velocity will be 0 because here it will just come to rest. Again, the time, I don't know and I don't care, so we're going to cross off the time. Now the acceleration will be negative, it will be a deceleration. A will be slowing down. So the acceleration, sorry to be quite messy here, the acceleration is based off mu r plus 2 mg sine theta. So again, it's F equals ma. So mu r plus 2 mg sine theta that'll give us the magnitude of this acceleration. Now from before, we worked out what μr and 2mg were in easier form, so let's just skip back for a second. So what we had here, we had that μr was 3.92 m log. μr, I'm going to put 3.92 m. And we also worked out what 2mg sine alpha was in simpler terms. So 2mg sine alpha, this one, was 11.76 m. And that equals ma. Again, now you can see that the m's will cancel. But of course it was 2ma, apologies. It's not just ma, it's 2ma, I do apologise. 2ma, not just 1ma. The mass here is 2m. I do apologise. So now, what we can do is we can calculate the new magnitude of acceleration. So a is 3.92 plus 11.76. Divide that by 2. Let's see what we get. Divide it by 2. 7.84. So the magnitude of the acceleration is 7.84 meters per second squared, but it's acting down the slope, so for us it's minus 7.84. So for this one, we can now use v squared equals u squared plus 2as again. So we've got this here. If I just neaten this off now, so hopefully you made a note of this, I'm just going to take this away. So that's been done with. So what's the extra displacement before it stops? So again, we can use v squared equals u squared plus 2as. So v squared, 0 squared, u squared, the square root of 7.84h squared gives us 7.84h. The squaring and square rooting cancel each other. Then we're going to have plus 2 multiplied by minus 7.84 times the displacement. So therefore, if we rearrange, S would be 7.84h divided by 2 times 7.84. That gives us 0.5h. So therefore, distance xy from x to this z place, it travelled h before b hits the ground. Then from z to y, we just worked out it goes a further 0.5h. So from here to here, that's a further 0.5h. So h plus a further 0.5h gives us 1.5h. Quite a horrible question, I'm sure you agree, but it's good practice. Doing the really hard questions is the best way to secure the best grades. If you can do the hard ones, the easy ones will seem like, relatively speaking, a doddle. So that's all from me. I think I've talked to you for far too much personally, but there you go. C'est la vie. So now over to you. My suggestions here are questions 3, 4, 5 and 6 from exercise 7F on page 152. Do those. Check your answers regularly as you're going through them. If you're stuck, just ask a neighbour. If that doesn't bear any fruit, ask me, either in lesson, on an email, or even in the comments section if you're really desperate. So thank you for listening. Thank you for bearing with me through that. That's quite hard going, but that's all it is for chapter 7 now. So wish it fond farewell, and I'll see you all soon, I hope. So have a good one, and goodbye until next time.